Hey everyone, welcome to episode 2 of Everyday Physics. Today we're going to be looking at torque and rotational motion with a bike wheel. The wheel here is connected to this axle, which is the pivot point. We have it taped at the top so we can see how many times it goes around. I'm going to apply a slight torque and spin the wheel. Now, as it spins, the wheel is going to slow down because it's going to have a negative angular acceleration due to a frictional torque, the opposite of the direction of motion. We know that the wheel spun 4 3/4 times, and it took 20 seconds to stop. The first thing I want to do is convert this 4 3/4 revolutions into a delta theta, which is the angular displacement. So all we have to do is convert that to the number of radians that it spun, which is just that 4.75 revolutions times 2 pi radians per revolution to get 19 pi over 2 radians. What we want to find is what my initial angular velocity was, what the angular acceleration is while it slows down, and the torque on it while it's spinning. The first thing that we're going to do here is draw a graph of angular velocity versus time. We know that the wheel starts at an initial angular velocity, which decreases at a constant rate until it stops at t equals 20 seconds. Now this is very much the same as solving for linear velocity and linear displacement, except now it's just angular. So the area under this graph is going to give us delta theta, the angular displacement, which we solved for at the beginning. So now we can see this graph as a triangle, this side being the initial angular velocity, this side being 20 seconds, and the area being delta theta. So we can plug in what we know and find that the initial angular velocity is 19 pi over 20 radians per second, or 2.98. If you're having trouble visualizing what this means, just keep in mind that 2 pi radians is 1 revolution, so pi radians per second would be half a revolution per second, and this is very close to that, so basically 1 revolution every 2 seconds. So now we need to think about, why does the wheel stop? If there was no unbalanced torque on the wheel would continue to spin. This is just like objects moving linearly. If there's no force acting on the object, it'll continue to move at constant velocity. So we know there must be some sort of torque on this wheel as it's spinning, and that has to be the opposite direction of the direction of motion. So I mentioned this earlier. The torque is caused by friction between the wheel and the axle. And friction always goes opposite the direction of motion. So we have our initial angular velocity going this way, and an angular acceleration caused by frictional torque going the opposite direction. That's why the angular velocity decreases until it reaches 0. Now, keeping this in mind, we want to solve for what this torque is and what the angular acceleration on the wheel is as it spins. So the first thing we want to do is draw a graph of angular acceleration versus time. Now, this is negative, and that's very important. The fact that this is negative means that the angular acceleration is in the opposite direction of the angular velocity. It means it's causing it to slow down. We also know that this is constant because it's caused by a constant torque, and the angular acceleration is given by the change in angular velocity over time, just like how regular acceleration is given by the change in velocity over time. Now we can solve for it. We know that the change in angular velocity is negative 2.98 radians per second. Again, negative, because if we're doing final minus initial, it's 0 minus 2.98 over 20 seconds, or negative 0.15 radians per second squared. Now the last thing to solve for is the torque. We know that torque is given in the equation angular acceleration equals the sum of the torques over I. I of the wheel is about 0.1 kilograms meters squared. The only torque in this case is friction. So if we plug that into the equation, we get that the torque is negative 0.015 meter newtons. Now I'm doing that because I want it to be clear that this is not Newton meters as in joules. This is not energy. This is a force applied from a distance away, not a force applied over a distance. I know rotational motion is a concept that confuses a lot of people. So before I close, I wanted to talk about how similar it is to linear motion real quick to help clarify some of that. The displacement, velocity, and acceleration of these work basically the same way, and you can solve for them the same way. The slope of the velocity time graph is going to give you the acceleration, and the area is going to give you the displacement. That's the same as rotational, where the slope of the angular velocity graph gives you angular acceleration, and the area gives you delta theta. When it comes to forces and inertia, it's also very similar. A force causes an object to move linearly. Mass is basically a measure of how difficult it is to move an object. A bigger mass means more difficult. And the acceleration equals the sum of the unbalanced force over the mass. It's very similar for rotational motion. A torque is something that causes an object to spin, and the rotational inertia is a measure of how difficult it is to spin the object. Angular acceleration is given by the sum of the torques over the rotational inertia. So there's a lot of similarities here, and if you can kind of see those similarities, it'll help clarify rotational motion for you. Hopefully this helps. Thanks for watching. Hopefully you enjoyed this video. Hopefully you learned something, and I'll see you next time.